Hi, welcome to video 5.1b, more derivatives of natural log functions. Okay, so they're just going to ask different questions. This is kind of a good review of the whole course. Find the equation of the tangent line to the graph of f at the given point, and then they want you to use the calculator to graph the function and the tangent line, and etc. Okay, so this is number 80. F of x equals sine 2x times ln of x squared, and you want to find the equation of the tangent line to that graph at that point. Nobody's asking you to graph this function, thank the Lord. Okay, so we obviously have a product rule going on here. I'm actually going to put them in parentheses so you can see that. So to find the equation of any line, we need a point, which they gave us, the point 1, 0, and we need the slope of the tangent line at that point, which is f prime of x at x equals 1. So I need to find the derivative. I'm going to use the product rule. I have the first factor times the derivative of the second factor, which is 2 times 1 over x, plus the second factor, which is my second parentheses, 2ln x, times the derivative of the first factor, which is this cosine of 2x times 2 by the chain rule. So we now need to replace all these x's by 1 because we're evaluating it at 1. That becomes the sine of 2 times 2 plus 2 times 0, because the ln of 1 is 0, e to the 0 equals 1. And 0 times, who cares what? It's 0 times. So we end up with a slope of 2 sine 2, and the point was the 0.10. We plug in the 0.10 and the slope into the point slope form, and we're done. Use implicit differentiation to find dy dx. So the question is the ln of xy plus 5x equals 30. So we're going to take d dx of each side. The first thing I'm going to do, I could do a product rule, but I don't have to because it's logarithms, and I can break up the ln of x times y into ln x plus ln y. Those log properties are there to make your job easier. Okay, so now I can take the derivative of d dx of ln x is 1 over x, d dx of ln y is 1 over y times dy dx, chain rule, plus 5 equals 0, and then you'll slowly isolate. You'll get dy dx equals negative 5 minus 1 over x, and you multiply that by y. 87 through 88 use implicit differentiation to find an equation of the tangent line to the graph at the point. So that's kind of a combo of the last two questions. This says y2. It should say y squared plus ln xy equals 2 is your curve, and you want to find the equation of the tangent line to this curve at the point E1. So again, I'm going to break up that ln of x times y into ln x plus ln y. So I have y squared plus ln x plus ln y equals 2. Take the derivative of each side. I'll get 2y dy dx. Don't forget, it's implicit. Plus 1 over x plus 1 over y dy dx equals 0. Bring all the dy dx's to one side, all the other things to the other side. That's the slope. dy dx is the slope, but we need the slope at x equals e. So we're going to take this expression and replace all the x's by e's and all the y's by 1's, because they told us the point E1 is on the graph. So I have negative 1 over e over 2 times 1 plus 1 over 1, which is negative 1 over e all over 3, which is negative 1/3 e. So that's the slope of my tangent line, and then I plug in the point. X1 is e and y1 is 1. Locate the relative extrema points of inflection. So of course you have to start with domain. Remember, you cannot take the log of a negative. I'm going to need my derivative, so that's going to be 1 minus 1 over x. Find a common denominator. That derivative will equal 0 when x is 1, when the numerator is 0, and it'll not exist when the denominator is 0, okay? But our domain at any rate is x has to be bigger than 0. So now we're going to place those numbers, that number on our number ray, because x is bigger than 0, so we have just the critical number 1 to put on our number line. And sure enough, if you plug in a number between 0 and 1, now you might find that complicated, but think of a number bigger than 1, like 4 million. So if you have 4 million minus the ln of 4 million, you're going to raise 2 to which power to get 4 million. Obviously, that power is less than 4 million, so you will get a positive answer. And then if you plug in, 1 over e, for example, you get negative 1, but anyways. So there's a relative min at x equals 1. Plug that into your original function. Your y value is 1 minus ln 1, which is 1 minus 0, which is 1. And therefore, we have a relative min at 1, 1. Now, they also asked for points of inflection. So from here, um, okay, I guess from here, right, this is what I did this. So this is 1 minus x to the negative 1. The derivative of 1 is 0. And then the derivative of negative x to the negative 1 is positive 1x to the negative 2, better known as 1 over x squared. It equals 0 never, because the numerator is never 0. It equals, does not exist when the denominator is x equals oh, sorry. It's not going to exist when the denominator is 0, which is when x equals 0. However, x cannot be 0 because it's not in the domain. So we have no crucial numbers, which means the graph is either concave up the whole time or concave down. You can easily look at this and see it has a positive numerator, and we're squaring a positive number on the bottom. We're going to get a positive. So it's obviously positive, the second derivative, which means the graph is concave up the whole time and therefore has no points of inflection. Okay, you should know your graphs. You should know the basic, this for many reasons. One, they could ask limit questions about them. It's really easy if you know what the graph looks like, and we'll be getting into area and volume very soon. So, y equals ln x, you should know, has a vertical asymptote of x equals 0. It rises slowly, quickly at first, and then tapers off, and it goes through the point 1, 0. As you can see, the domain is x is bigger than 0. If you put a minus 1 in front of it, then it's going to reflect that graph over the x-axis. Okay, so if I take this graph and flip it over this axis right here, this will end up down there, and that'll end up there. Also, what's good about the graph is you're able to answer questions about limits very easily. If you look at the picture and they go, what's the limit as x goes to infinity of this of ln x? Well, obviously, if I move to the right, it's just getting bigger and bigger. It's doing that slowly, but it is getting bigger and bigger, so that's infinity. Limit as x approaches 1 from both sides of ln x is 0, because that 0.10 is the x-intercept. And the limit as x approaches 0 from the right of 0 is actually negative infinity. Okay, what else could they do to mess with the graph? They could, instead of having the negative on the outside where they flip the graph over the x-axis, they could have it on the inside, which flips it over the x-axis. So if I took this special graph, if I folded it along the y-axis, I would end up with this, which is exactly what that picture is. So the AP loves questions using the graphs of log functions. I don't know why. For example, they'll have limit questions. They'll have find the equation of a tangent line. They'll have find the area later, which we'll do, and find the volume later, which we'll do. Okay. So right now it's just a review of graphing log functions. So negative 2 ln x, the 2 will make it steeper. The negative will make it flip over the x-axis. So if you have this graph and you flip over the x-axis, you should see that it would look like that. Still the same vertical asymptote, still the same x-intercept. Y equals the absolute value of x means that whatever happens on the right of the y-axis when x is positive is going to happen on the left of the y-axis when x is negative, because you're going to take the absolute value of that negative. So I take the right portion of this graph and simply flip it over the y-axis. Now, now what happens, y equals the absolute value of x, of ln x, means that whatever was above the x-axis will stay above the x-axis, but if you had something below the x-axis, it's now going to flip up. So if you take this part of it was already above, so that doesn't change down here, but this part is below, so it's going to flip it over here and be pricing up. Okay, plus 2 is going to move the graph up 2. It's not like we have a vertex that we're using here, so what we can do is look at the most important point on the graph, which I would think if we go back to the main graph at the beginning, you'll notice it rises very quickly, and at that 0.10, all of a sudden it starts increasing, but at a decreasing rate. So if I take that 0.10 and simply move it up 2, it's now at the 0.12. This, of course, will move it right 2, which means the vertical asymptote, which used to be at x equals 0, will now be at x equals 2. And then it moves right 2 and up 1, so this 0.10 moved right 2 will put it at x equals 3, and up 1 will put it at y equals 1. So not that hard. We already talked about a negative on the outside flips it over the x-axis. And if you have both, it's going to flip over the x-axis and the y-axis, the original graph. And you should get this picture right here. All right, so find the equation of the tangent line. Again, same idea. There's your equation. Remember, if you have the ln of x to a power, you can pull that power on the outside. So it'll be easier to differentiate now. We're going to need the point, which they gave us. We're going to need a slope of the tangent line, which is the derivative, which is why I'm over here doing this. So the derivative will be 3/2 times derivative of ln x is 1 over x. You're going to replace the x by 1. You've got your slope, you've got your point, you've got your line. Pretty straightforward.